Hello everybody, I am Roberta Lima and I will present the work 6 Sleep Oscillations in a Stochastic Multiphysics System. The work was done by me and Rubens Sampaio. We are both from PUC-Rio. I'll start this presentation making a deterministic analysis of the dynamics of the electromechanical system with ray friction. We're gonna see how 6 sleep oscillations are affected by electromechanical coupling in the dependence between the duration of the stick modes and the position of the mechanical subsystem of the electromechanical system. After, we'll construct a probabilistic model to the system. And finally, we'll construct a stochastic model to the system response. In this model, we are interested in the analysis of the stochastic dependence between the duration of the stick modes and the position of the mechanical subsystem of the electromechanical system. This way, in the deterministic analysis, we verify the deterministic dependence between these two variables. After, we analyze the stochastic dependence between them. To quantify the uncertainties in the system response, that is, to quantify the stochastic dependence, we use joint histograms. Let's start talking about what is an electromechanical system with ray friction. An electromechanical system is composed by two coupled subsystems, one of them electromagnetic and the other mechanical. The electromagnetic can be, for example, a DC motor. And as we're talking about electromechanical systems with ray friction, in the mechanical subsystem, we consider the existence of ray friction. Coupling between the two subsystems means much interaction between them. That is, each subsystem affects the behavior of the other. Consequently, the ray friction affects and is affected by the electromechanical coupling. The system analyzed in this work is composed by a DC motor coupled by a mechanism called squat-walk to a cart. How does this mechanism work? Attached to the motor axis there is a disc, and at a distance d from the center of the disc there is a pin. This pin slides into a slot in a plate which is attached to the cart. The squat-walk transforms the rotational movements of the disc, which we call alpha, into a horizontal translation of the cart over a rail. We call the position of the cart as x. We consider the existence of ray friction between the cart and the rail. The electrical current in the DC motor is called C, and the imposed source voltage is V. The initial value problem that gives the dynamics of the DC motor is given by two coupled differential equations. In one of them, we'll have the derivative of the electrical current, and in the other, the acceleration of the disc. The problem has three initial conditions, two of them mechanical and one electrical. A source voltage V is imposed into the electrical circuits of the motor. This source voltage oscillates around V0 with amplitude V1. It has frequency omega V and phase phi. The equation of motion of the cart can be obtained by Newton. The product of the cart mass and its acceleration is equal to the sum of forces acting over the cart. We have two forces acting over the cart. The coupling force between the cart and the motor, which is highlighted in blue, and the frictional force between the cart and the rail, which we call Fr. It is possible to write a relation between the coupling force and the coupling torque. And it is also possible to write a constraint between the position of the cart and the position of the disc due to the squat-walk mechanism. Deriving twice this constraint and substituting it into the cart equation of motion, and after substituting the coupling force into the expression that relates the coupling torque and the coupling force, and finally substituting the coupling torque into the initial value problem of the DC motor, we obtain the initial value problem of our electromechanical system. The initial value problem of our electromechanical system is given by two coupled differential equations and three initial conditions. We have also parametric excitation. This parametric excitation is caused by the terms highlighted in blue. The frictional force is modeled as Coulomb. When the cart velocity is positive, the frictional force is negative. When the cart velocity is negative, the frictional force is positive. When the velocity is zero, the frictional force can assume any value in this interval. Please observe that there is no functional relation between the frictional force and the cart velocity. With this model of friction, the system response can be composed of a sequence alternating stick and slip modes. Stick occurs when the cart velocity is zero and the frictional force is in this interval. Sleep is everything else. Here, I show a possible sequence of stick and sleep modes in the system response. We have the first stick, after the first sleep, then the second stick, and so on. The parameter of interest in this sequence is the maximal stick duration. We're gonna find an analytical approximation to this variable. To find this approximation, let's see what happened during stick modes with the equation of motions of the electromechanical system. During stick mode, the car does not move. It has velocity equal to 0, and the disk is stuck. Thus, in the equation of motion, we can cut the terms that are highlighted in red. After cutting the terms, we get just one differential equation and one algebraic equation. The initial value problem loses one differential equation. Thus, during stick modes, the system is governed by the dynamics of the motor. The sum of forces that act over the cart is 0. The coupling force is balanced by the frictional force. The stick lasts until the absolute value of the frictional force reaches its maximal value. During stick modes, we need to integrate this initial value problem that is composed by just one differential equation with just one initial condition. Please observe that the initial value problem involves just electrical parameters and is valid for t between t1 and t2, that is, the instance of the beginning of a stick and the instance of end of a stick. We call the angle of the disk in the beginning of a stick, alpha in t1, as alpha star, and the current in the beginning of a stick, C in t1, as t0. The solution of the initial value problem during the stick modes, that is, t between t1 and t2, is given by this expression. If we neglect the influence of the initial condition t0, the solution of the initial value problem can be approximated by this expression. Recalling the conditions to have a stick, we discovered that the stick will land when the currents reach this value. Then it is possible to discover T2, the instance of end of a stick. This way, we know an upper bound for the stick duration. Now, let's see the influence of the position of the disk, that is, the angle where the disk is stuck, alpha star, during a stick, and the influence of the value of the friction coefficient in the upper bound for the stick duration. We verify that when alpha star is low or is near P or 2P, there is no stick. When alpha star is P over 2 or 3P over 2, the stick lasts more. We have this behavior for the frictional coefficient equal to 0.1 until 0.5. When we increase a little bit the value of μ, for example, μ equal to 0.6, the stick can last forever if alpha star is around P over 2 or 3P over 2. Please observe that the stick duration depends on the position of the disk. These two variables are dependent. Now let's go to the stochastic part of the work. We'll construct a probabilistic model to the source voltage and to the initial condition of the angle of the disk. We'll model as uniform random variables over 0 and 2p the phase of the source voltage and the initial condition of the angle of the disk. Due to the uncertainties, the system response becomes stochastic and will have a stochastic sequence of sticks and sleep modes. In this sequence, we model as discrete random variables the number of sticks and the number of sleeps. We model as continuous random variables the instance at which the sticks begins, the duration of the sticks, and the position of the disk when the sticks begins. We are interested in D1 and A1 star. They are related in red. We'd like to verify how these two variables are related, that is, their stochastic dependence. To make such analysis, we're going to perform multi-color simulations and construct scatter plots and joint histograms for their samples for two different values of friction coefficient. We're going to consider μ equal to 0.3 and 0.5. In the multi-color simulations, we integrated the initial value problem 10,000 times for each value of μ. The CPU time to make the computations was around 30 hours, and amount of generated data was around 20 gigabytes. This shows that our problem is a big data problem. The parameters values used in the simulations are given in the table, and we used Hange-Kuten method of fourth and fifth order as time integration scheme. A small time step was required in order to determine the instance of transition between the phases. Here we see one realization of the system response. The instance of beginning of sticks are highlighted with black circles, and the end with green squares. Now, let's see for the friction coefficient 0.3, the normalized histograms of the samples of A1 star and D1. As we know, A1 star and D1 are dependent random variables. To verify this, we plotted the normalized joint histograms of the samples of A1 star and D1 and compared it with the product of the normalized marginal histograms of A1 star and D1, which I showed before. Please observe that these two histograms are completely different, proving the dependence between A1 star and D1. We completely lose the support of the histogram when we make the product. But this was predictable because we computed previously the support when we computed the upper bound for the sick duration. Here I show the upper bound and the scatter plots of the samples of A1 star and D1. Please observe that the upper bound defines the support of the joint histogram. Now let's see a similar analysis for the friction coefficient equal to 0.5. First, we see the normalized histograms of the samples of A1 star and D1. After, we see the normalized joint histograms of the samples of A1 star and D1 and compared it with the products of the normalized marginal histograms of A1 star and D1. Again, we'll see that they are completely different, including the support. Finally, we'll see the upper bound for the sick duration and the scatter plots of the samples of A1 star and D1. Please observe again that the upper bound defines the support of the joint histogram. Now, the final remarks of the presentation. In the deterministic analysis, we analyzed the dynamics of an electromechanical system. We verified that this dynamics is given by initial value problem comprising a set of coupled differential equations, and we determined how cyclic oscillations are affected by electromechanical coupling. We observed that the maximal cyclic duration depends where the disk is stuck. In the stochastic analysis, we quantified the uncertainties of the system response by joint histograms, and we quantified the stochastic dependence between the duration of the cyclic modes and the position where the disk is stuck. If you're interested in the subject of cyclic oscillations in electromechanical systems, you can find more details of the deterministic part of this work in the paper that I show here. Thank you for your attention.